All right, so Calculus 30L class, Advanced Integration. We're going to be looking at integration by parts today, something you've probably never heard of. So I'm going to just give a quick introduction. Guys in the back, quiet. Thank you. Quick introduction. It's in Chapter 11, Section 4 in your Red Stewart text. This is what it starts out as. The brief introduction here, integration by parts. When we talk about integrating, really the only type of integration that we've done so far is the U substitution. Okay? So if we have a single term, we can find the integral of that, no problem. Okay? There's a lot of different shortcuts. There's a lot of different formulas that we know about integrals. We know about integrals. But when we have the chain rule, that's when we do U substitution, right? If we have a function and part of its derivative, the derivative without maybe just a constant, right? Just missing a constant. When you have the function and at least part of its derivative present, then you can do U substitution. But when we have something like a product rule where you have a function but you don't have any part of its derivative present there as well, U substitution doesn't cut it. And we're going to look today at something called integration by parts. Now, to introduce integration by parts, what I'm going to do is I'm going to take two functions that are multiplied and we're going to take the derivative of them. Okay? So when we take the derivative dx of this function, represented by product of two smaller functions, we do the product rule. So what does the product rule look like? The derivative of the first, and I'll just use Newton's notation over here, times the second, plus the first times the derivative of the second. Okay, is this all making sense? Is this familiar to you? Okay. All right. Now, if we take the integral now, if we take the integral with respect to x of everything, and I'm just going to put big brackets around everything here, and of course that applies to each term separately. Take the integral, and I'll just do this anyways. Take the integral of everything. This is sort of what we have. What we end up with is this. The integral of the derivative of something is just equal to that same thing, right? So we undo this. So we get this. All right? One extra bracket in there. On the other side, we have this integral of the derivative of one of the functions times the function, the original function, plus also, and this is all dx, of course, plus this over here. So we have a function, its derivative, okay, and derivative and a function. Now, if we rearrange this just a little bit and we pull out, we pull one of them out, doesn't matter which one, okay, but we isolate for one of these integrals, and let's go back to our textbook here. Insufficient data. Oh, really? There we are. Okay. So you see what we've done here? This is sort of what we've done here, taking the derivative of all this with the product rule, okay? And we're going to isolate, so let's do the same as this one. So we have the original function times the derivative of the second, okay? So where's the original function times the derivative of the second? That's this one here. So if we isolate this, okay, we get the derivative of f of x times g prime of x equals f of x times g of x minus the integral of this one that remains. Okay, so I know what you're thinking. You're thinking, how does that simplify anything? How does that simplify anything? Well, here's the idea. Here's the idea. One of these integrals, either this one or this one, and again, it doesn't really matter which one you isolate for. One of these integrals will be difficult to solve or to find the solution for, and one of them will be fairly easy. Okay, and so of course this is just original functions right here. So this part is super easy. It's the function that just shows up, and this one we're hoping this integral is easier to integrate than the original one. Okay? So really what we're doing is we're taking a massive sort of complicated integral and we're splitting it into parts, right? Integration by parts. And so we're hoping that both of those parts that we're splitting it into will be easier to deal with than the original one. Okay? Now, I don't know if that gives you any comfort right now that we're taking one integral and we're making it into two things, but hopefully the one part should be simpler. So let me give you an example. Okay? So notice what we have here. We have on the original side, right, that we're trying to take the integral of, we have the original function here is going to be a function and a derivative. So one is going to be sort of f of x and one is going to be g prime of x. Okay? And so what we have to do is we have to figure out, which one is which. And so when you have this integral right here, x times e to the power of x, when we're thinking of derivatives, which of these would is really easy to take the derivative of? Well, both of them are really easy to take the derivative of, right? So which one, how would we follow this right here? First function is going to be this, right? The second function is going to be the derivative. So this is going to be the derivative. All right? So f of x is going to be x. Okay? So what I'm going to challenge you to do is just to write f of x, f prime of x, just like I've done here, g of x, g prime of x. Okay? So if we look over here again, on this left side, the first one's going to be f of x, the second one is going to be g prime of x. And so g prime of x is actually going to be down here. That's going to be e to the power of x. Everybody see that? Everybody see what I'm doing? Okay. Now what is the derivative of x? 1. What is the integral of e to the power of x? Right on. It's e to the power of x. Okay? So we can now, let's just see here. I'm going to leave this up here, and I'm going to explain this as, let's transfer this over and this over. Okay? So what's f of x? Well, f of x is just x. Right? That's right over here. What is g prime of x? Well, that's e of x. What is g of x then? That's this one. Right? So e to the x. So f of x and g of x. F of x and g of x. You see that? Minus, okay. Now what is the integral? So we've got the integral of f prime of x and g of x. So let's do this here. What's f prime of x? 1. What's g of x? Times e to the x dx. Now, if you look at this, this is much simpler to integrate, isn't it? Because it's just e to the x. It's the integral of e to the x. That's the way that works out. So that 1 is in effect gone. So our answer then is x times e to the x minus what? What's the integral of e to the x? Just e to the x. Plus c. And if you want, you could take e to the x out, x minus 1, plus c. That's the expression of the integral. Everybody see that? Okay. So there's a couple things here. I mean, this is integration by parts. What I'm going to show you right away here is a bit of a, I don't know if it's a shortcut, but it's an easier way to do this. Like, I don't really like doing this and memorizing all this. To me, I don't like doing that. There is an easier method. There's an easier method that I really like to show students and really like to use. It's called the DI method. Okay? So now we're going to do the same question, and I'm going to show you the DI method. Now, what does the D and the I stand for? What do you think?
Detective.
Not detective, no.
I was going to say detective.
What's a D word that I just used extensively? Thank you. Derivative. Yeah. Okay. Think about the main branches of calculus, right? Differential and what? Okay. Okay. Derivative and integral. Okay. So the D and the I, and you're going to make just a little kind of a little chart over here. Okay. D I. Now, as we know, integrating by parts, if we have two functions here that are multiplied together, And notice that the derivative of e to the x is e to the x. We don't have the derivative here, so use substitution is not going to work very well. That's why we're doing this. Okay? So one of them is going to be a derivative, and one of them is going to be an integral. Or we're going to instead differentiate this column, and we're going to integrate this column. Okay? So when you're doing this, you want to pick one of these that's easy to integrate or easy to differentiate. All right? So which one would be easy to integrate out of these two? And you probably know which one, right? Because we did this last time. But do you want to integrate x and then integrate that again, integrate that? Or is it easier to integrate e to the power of x? Which one's easier? Do you want to go 1/2 x to the x squared and then go up from there? No. So this derivative is really easy to take the derivative of x. And e to the x is really easy to integrate. So that's how you decide which goes where. Now, there's a couple other little things that we need to remember to do, and that is this. We need to just arbitrarily put a positive sign right in front of the first row. And we're actually going to be doing rows of this. Okay? Rows. So plus and then minus and then plus and minus. So let's make 3 or 4 rows.
How many plus and minus?
Doesn't matter. 4. I just did 4. Let's do 4. Okay. So now here's the easy part. We take the derivative of this right here, x. What's the derivative of x? 1. Okay. Now what you need to do here in this, so this is type 1 of the DI method. It's sort of type 1. This is the easy one where we can actually differentiate down to 0 eventually. Okay, and that's what you want to do. You want to actually keep differentiating until you get to 0. So what's the the derivative of 1? Is 0. Okay, so that's great. That is really going to help us here. Now we move over to the other column and we integrate. So what is the integral of e to the x? Well, super easy. That's e to the x. What's the integral of that? E to the x. Okay. When you get to the same row as the 0, you stop. Right? All right, so now we have derivatives and integrals. Now, this is the cool part. So what you do is you start here. You always start here with the derivative. Remember, the d comes first in the DI method. You start with this one, and then you skip down to the second row. Because remember, in the integration by parts formula, we have the derivative and the function, right? We have derivative and function, or sorry, let's have the function and the other function, right? And so how do we get that? Well, if this is a derivative, if this is the function and this is the derivative, then I integrate to get both functions. So this is f of x here, and this is g of x right here. You see that? So you always take the top one and you draw an arrow to the second row over here. And then you do the same thing. You go from the second row on this side to the third row on this side. And when you see a 0, then you can stop. Because this is going to be 0 times whatever, and it's going to be 0 times whatever, right? So we're not concerning ourselves with this. Now, if you take into account the signs here, this is basically just telling you what this integral is equaling. And this is the shortcut for integration by parts, the DI method. So the answer to this is simply, remember, it's f of x times g of x. So it's going to be this x times e to the x. And that's a positive. And then guess what? We're going to minus. And why do we put that minus there? Because look at the integration by parts formula. There's always a minus there. So that second row is going to be minus 1 times e to the power of x. It's e to the power of x. And then when you get to the 0, right, we're going to stop. And so you add c, and you're done. And that's the same thing that we got in the above question. Okay? So that's right here. And you don't have to factor. But anyways, so integration by parts, you can follow this now very messy formula here. You can follow this formula and you can do this little array of function, derivative, but you know what? I like the DI method a lot. So let's do another example of the DI method. And I just threw up this table of indefinite integrals for you. So we can check this if we want to. Okay, so remember, let's think about substitution. Can we do, well, we don't want to do u substitution for 3x. We wouldn't want to do u substitution for cos because we have no sine or anything. So u substitution is out the window. We do have two functions that are multiplied together, and so let's try and attack it by integrate by parts, okay? That's what we're going to do. So let's do the DI method. Let's have a d over here and an I over here. Okay, and let's do a plus minus plus minus. And I'm looking at this, and of course, if you have a monomial as one of your functions, that's always going to be the derivative, right? Because that's going to get us down to 0 within a few steps. So you're going to put the x here, and you're going to put cos of 3 of x, cos of 3x, sorry, over here. Now, integrating cos of 3x, not insane. It's not terrible. It's maybe not the easiest thing in the world to do, but it's pretty easy, and we'll take a look at the chart down here. But that's what we put in there first, okay? So now we differentiate. The derivative of x is 1. The derivative of 1 is 0. We stop. If you ever get a derivative in the 0 in the derivative column, you stop. So now we move over to the integral column. What is the integral of cos of 3x? What's the integral of cos of 3x? So the integral of cos is going to be what?
1 over sine 3. 1 over 3 sine.
Okay, so the integral of cos is it positive sine or negative sine? So it's over here, right? You can look at cos, it's positive sine. So sine of 3x. But we have to account for the fact that we have a number here that we're going to have to multiply by, right? So we have to do, I think, sorry, you said that, 1 over 3,
Yeah.
sine 3x. Okay, is everybody good with that? All right, so that's the second row. Now we need to do a third row here because we have to line up with this 0. So I'll just move this 0 down a little bit. So what's the integral of this now?
Negative cos.
So the integral of sine is, that's correct, negative cos of 3x. So here's sine, you see, negative cos. And we have a 1/3 here already, but we also have to, when we integrate, we have to account for this 3. So we have to do literally 1/3 and then times another 1/3.
Really?
Yeah, really. So, whoops, I erased too much there. So this is going to be negative 1 over 9 cos of 3x. All right, so we've done row 1, row 2, and row 3. Because this is in line with the 0 here, I can stop. Okay? So you guys tell me, what do I write over here? So this integral equals what? Where do I start? X times 1/3, okay, 1/3 sine of 3x. Very good. Minus, yeah.
Why don't you just make it positive?
Okay, so we could make this positive because it's a negative and a negative. So plus
Just take it 3.
1/9 cos 3x. Does that look right? Okay. Now plus c, we don't want to forget about plus c because it's an indefinite integral. But now I can combine, I can simplify this a little bit, right? So it's going to be what? 1 over 27 x. Sorry? 1/3 times 1. Oh, my bad. There's a plus there. Sorry. Let's just do this as x times 1/3 sine 3x plus 1/9 cos of 3x plus c. So no, we can't really simplify that much. You could get rid of this little dot there if you want, but no, not really. You could do x over 3 or whatever you want to do. Okay? So, yeah, you guys just rewrote the same thing, I guess. So that, let's see. Let me just double check now. I should be checking my notes here, of course. The notes that I painstakingly made here, yeah. Plus c. Okay. So any questions about that?
No.
Okay, so why don't you guys try one on your own here. So I've kind of got this set up here for you. So just ignore that. It's the integration by parts here. Okay, so you guys try this one. Okay? Try this one. Go. Okay, so your chart should look like this. X squared the derivative, sine x the integral. Work down. Again, we get to 0 here, so this is the row that we stop, right? So the expression of this, using integration by parts, using the DI method to help us kind of sift through this, we're going to go positive x squared minus cos x. Am I subtracting or am I multiplying? Right, we multiply. And then I do minus 2x times negative sine x. And then so I did first row. I did the second one. And now I'm doing this one. Plus 2 cos x. So when you simplify all that, you get negative x squared cos x plus 2x sine x plus 2 cos x. When you hit the 0, you can stop, right? Plus c. Don't forget your plus c. Okay? DI method. All right. Any questions? Okay, so the second half of this lesson is integration by parts DI method type 2. Now, the type 2 happens when you actually, these things don't kind of get down to 0. Okay, if they don't get down to 0, then you have a bit of an issue. Or if it takes, if it's very difficult to integrate or to differentiate either of them for many steps. So type 2 is where you don't get down to 0 very easily. So let's take a look at this one. Now I have something over here written too. Liate, okay, L-I-A-T-E. And this is actually the order in which you would choose which one to be the derivative in the DI method. So if you have two functions and you're not really sure which one to choose, which one should be the derivative, which one should be the integral, then you think back to this little memory mnemonic here, liate, and logarithms you would choose first. So natural logarithms, of course, you would choose first. And then inverse trig functions would be second, algebraic terms would be third, trig terms, and exponentials. Okay, so that's the order in which sort of we choose which one would be the derivative.
Wait, what if you have a logarithm?
Natural logarithm, that's what the logs are. Yeah. These logs would be ln. Okay? All right, so which one comes first in this list? The natural log. So actually we're going to choose this one to be our D and this one to be our I. Okay?
Mr. Martin, please call 205. Mr. Martin, please
The
call
derivative is going to be
205.
ln of x. The integral is going to be x to the fourth. Plus, minus on the side, remember? Okay, now, here's the thing. Because this is type 2, this is not going to happen exactly the same way as the other one. And I know what you're thinking. You say, Mr. Maxwell, we could probably get this down to 0 pretty easily. And you can, right? You can differentiate this until we get to 0. But it's going to be 4 or 5 steps down the road. And to integrate ln of x, okay, that's not happening. So you're not going to want to do that. Instead, you're going to want to go this way. What's the derivative of ln of x? And if you need to check back to your chart, you should have a chart in your book here. So what's the derivative of ln of x?
1 over x.
Okay, so the derivative of ln of x is going to give you 1 over x, right?
Yes.
Whoops. So this is going to be 1 over x. Okay. Now what's the integral of x to the fourth? Very good. 1/5 x to the fifth. That's the integral. All right. Now, Okay. So with this method here, again, we don't have to get anything to 0. And as a matter of fact, boys, listening? As a matter of fact, we can stop right here because we are easily able to integrate a row that's on our table. So look at this. Remember, this is an integral row. So this is actually this times this, and we're taking the integral of it. The DI method goes it crosses rows, and then we don't have to take really the integral, right? Because we're doing this already. But in this case, if we can integrate a row fairly easily, then we're going to stop right there. Okay? So we're going to do this. We're going to do, the first part is going to be the same. Okay? So we're going to have this right here, including the positive. We're going to write this down. So 1/5 x to the 5th times ln of x. That's going to be the first thing we're going to do. But then we are going to do this. We're going to do minus this row, and we're going to do the integral of that. So minus the integral of 1 over x times really x to the 5 over 5, right? So each row is actually representative of an integral. Now, why would I choose to do that? Well, you would choose to do this because if you notice that the product of these two can easily be simplified into one single monomial term, and that's actually going to be pretty easy to integrate. So 1/5 x to the 5th ln x minus, this is going to be the integral of, what's x to the 5 divided by x? Yeah, it's just going to be, 1/5 x to the 4th. And there you have a single monomial term now, and that's going to be pretty easy to integrate. So, you guys are already kind of figuring that out already. So we add 1 to the exponent, and we divide by that same number. So that's going to be 5 times 5 down there, so that's going to be minus 1 over 25 x to the 5th. And then plus c, and you don't have to factor anything out or do anything more than that.
Wait, that's it?
Wait, that's it? Yeah, that's it.
Wait. So after, how do you know when to stop?
Okay, so how do you know when to stop? Good question. So in the first method, we always stopped when we hit a 0. But remember, that was 2 or 3 rows down, and you could always integrate 2 or 3 rows. Well, if we go much further than this, okay, we might run into some difficulties in the next couple rows. So if you get to a row that can be multiplied and simplified into one single term, like this, or when you can integrate a row fairly easily, like let's say we have a function and its derivative that are in the same row, that's when you stop. Okay, so if you kept trying this and kept differentiating this and kept integrating this side, and you realized, hey, you know what, I'm not getting to 0 and it's getting super complicated and I don't know when this is ever going to end, then go back and look for a row beneath the first row, obviously, but either the second or third or fourth row that you can maybe combine those terms by multiplying and integrate that term. Okay? So when you can integrate a row fairly easily, that's when you stop, and that would be, you know, in circumstances like this. Okay? So if you look at the let's see. If you look at our other ones here, okay. So just check this out. If we had this row, or this part right here, right, and then really we're multiplying by the integral of this row, right? The integral of this row is actually this right here. So sorry, we're not multiplying, but we're adding. So this is a row that we can integrate. But we just went ahead and integrated this because this is 0, right? Then we're going to stop anyway. So the DI method works if you hit a 0 in the derivative column, or if you run into a row that's pretty easily integrated.